Before we discuss how to analyze pipes in parallel, it is important to briefly mention how one analyzes the hydraulics of different pipes in a series. The figure shown here is a section view of 3 pipes laid in series. The first pipe has a different diameter, roughness, and length from the second, which in turn is different from the third pipe in the series. These pipes are joined by reducers that allow the transition between each diameter. By the way, because water can flow in both directions, we call all transitions between different diameters a reducer. The head loss between point A and B, shown here, is simply the summation of the head losses in each pipe and the minor losses between points A and B. That's it. Pipes in parallel, however, present a different challenge. For example, we have a system shown in plan view here where there is a flow rate entering a junction that splits the flow into 2 pipes, pipes A and B. If the diameters, lengths, and pipe roughness are the same between the 2 pipes, then we can easily estimate the flow in each pipe as being half the flow rate Q entering the system. However, it is more often the case that the diameter, length, and roughness of the pipeline are not the same. In this case, the flow rates in each pipe are not assumed to be equal, which means we need an approach to determine the flow rate in each pipe. The first tool that we have to find a solution is conservation of mass. In other words, the sum of the flow rates in both pipelines is equal to the Q that entered the system. The second tool we have is conservation of energy. We express this as the head loss in pipe A being equal to the head loss in pipe B. In other words, the amount of energy lost in pipe A, regardless of the diameter, roughness, or length of pipe A, is going to be the same as the head loss in pipe B. How is this possible? Well, water will travel the path of least resistance. In this case, let's say the water passing through A arrives at the end junction with greater energy than the water in B. This means that the water in A will push back against the flow rate in B until the flow rate decreases enough to make the energy losses equal. Another way to think about that is if the head loss in pipes A and B were not equal, then the result would be that the 2 different pressures trying to abide in the same place when the fluid stream joins up again. That is not possible unless there is some barrier of some sort to prevent the 2 flow rates from interacting. Ultimately, there will be just one pressure head at the junction as the 2 flow rates join back together. Calculating the head loss, we can use one of the head loss formulae previously covered. In this case, I will use the Hazen-Williams equation. Because the head loss in A is equal to the head losses in B, we can set the 2 head loss calculations equal to each other. Looking at it this way, we can see that the pipe characteristics are given for both pipes A and B. And I will represent this as Rs of A and Rs of B. Therefore, the unknowns in these expressions are the flow rates, which written this way allows us to solve for Q in terms of the other. With one Q in terms of the other, we can substitute this expression into the conservation of mass equation written earlier and then solve for Q in pipe B. Once we've done that, it's pretty simple to calculate the flow rate in pipe A and then determine the head loss in both pipes. If we introduce a third pipe to the system, then we can approach the solution in the same way by using conservation of mass and by setting the head losses in each pipe equal to each other. The unknowns are still the flow rates in each pipe. In other words, we have 4 equations and 3 unknowns. Also doable, but the math gets a little long-winded. Now consider the reality of a pipe network where there are not merely 2 or 3 pipes, but many pipes and many analysis points in the system. Therefore, the approach of simultaneously solving this many equations with this many unknowns is not feasible from a commercial standpoint. We need a better method to simplify the process for us.